Michael is a world-renowned researcher in a lot of disciplines, like visual computing, and I am very excited that you have the opportunity to hear what he does. He is a recipient of the most prestigious award in Europe. It's called ERC, European Research
Council. That's the grant.
Council. So, and it's not so often you meet people who received such an award. So, but you have met such a person. Here he is. So enjoy, and I will say goodbye for now. All right? So see you tomorrow. I will be talking about program verification. Goodbye.
So thank you guys for coming again at this late hour on Saturday, and it's actually my pleasure to talk about some of the cool stuff, which I think that is cool that we are doing in Switzerland. So I'm also affiliated with Intel, the perceptual computing lab in Israel. That's a long story. I will probably say a few words about this. So maybe the title of the talk is a little bit pretentious, to start thinking in 3D. But I hope I will try to convince you that dealing with 3D data is, geometric data is interesting and exciting. So let me start with this movie. I don't know how many of you have seen it. It's called Minority Report in English, and this is one of the most famous scenes in the movie, where Tom Cruise is manipulating some huge holographic screen with his hand gestures. So basically, the action of the movie, if you have not seen it, it's some dystopic future somewhere in 2050s, so 50 years in the future. And probably the creators of the movie were too skeptical about the abilities of computer vision to do this thing that we call hand tracking and gesture tracking, that they equipped Tom Cruise with these light gloves. You see that his fingers actually illuminated, which simplifies a lot the problem of tracking the finger positions. So when I watched this movie first time, I was still, I just finished my undergraduate studies, so I was starting my master degree. And the topic of my master research was 3D face recognition. So basically, how to recognize a person by the geometric structure of his or her face. And basically, at that time, slightly more than 10 years ago, if you wanted to acquire a 3D object, a 3D surface, basically, there were, of course, some scanners that could do it, but they were outrageously expensive. So we had to build our own system. So that was in Israel, where I did my studies. And this is how it looked like back in 2002. So you can see this is a projector, this is a camera, and this is some user interface. So basically, the user could approach this system and have his or her face scanned, and basically verify whether it's this person or some imposter. So fast forward to 2010, Microsoft came out with a very successful product called Kinect. So this was an add-on to Microsoft Xbox, which allowed, the main purpose was for gaming, and it allowed to control games with your bare hands. So you could basically move your hands, and it could recognize, actually could fit a skeleton to your body. And you can think more or less the future reality of Minority Report came true actually much way before it was planned, and actually with a much more sophisticated technology, because there is no need for any light gloves that Tom Cruise was wearing in that movie. And basically the main difference that made this a successful product was a 3D sensor that was compact enough to be placed in your living room, and was reliable enough to be manufactured in millions of units. And actually the technology provider was an Israeli company called PrimeSense that you might have heard about 2 years ago. It was acquired by Apple. So I myself was involved in another Israeli company called InVision. So basically we tried to take this vision further to make a 3D sensor that would fit into the bezel of your laptop, so you would be able to fit it in your computer. And we were acquired by Intel in 2012. And this became what Intel calls RealSense. So it was actually unveiled in Consumer Electronics Show in Las Vegas. So the sensor, I brought it here, looks like this. So it's very tiny thing that allows you to capture a 3D object from certain distance. So this goes into your laptops, and it allows you to do, for example, what Kinect did with a much smaller form factor. So if Kinect was the first time that 3D sensing became affordable, then with RealSense, at least that's the hope, that 3D sensing will become ubiquitous. Okay, so if you are fans of Big Bang Theory, then
what's that?
In 2004 there was an advertisement using one of the characters from Big Bang Theory.
Humans. Focus on me. Focus on the guard. Don't tell anyone what you see in here. Have you seen what's in there? They have
Intel. This is where it all changes.
So that was in 2014, about a year ago. I just downloaded from YouTube another advertisement. This is from Lenovo, which is one of the OEMs for Intel.
Video games. We're shown a fantastic interactive world full of possibility. Video conferencing is commonplace. People working and talking together, each adding graphics, different backgrounds, and personal data to create a richer communication experience. And when we watch them work on their computers, they use their hands and body to navigate through software, websites, and maps, pushing and pulling their data. Because it's a physical thing they can now shape. In the future, there's no distinction between digital and real, because devices can now easily scan physical objects to appear in software and games. A photo can be a 3D printed figurine, a sketch, the first stages of a prototype. This is not tomorrow. All this is possible right now because of Intel RealSense technology. Lenovo and Intel have innovated together to integrate the Intel RealSense 3D camera into the ThinkPad E550, ThinkPad Yoga 15, and the Lenovo B50 all-in-one. And with the world's biggest developers already releasing RealSense-ready software, the move to a more physical digital experience is not about to happen. It already has.
So long video short, basically maybe some of the visualizations that were shown here are more conceptual, but I think the bottom line is that this is not the future technology. This already exists. And you can actually, at least in the United States, you can walk into an electronics store and buy basically all the famous or all the major brands like Lenovo and Asus and Acer, HP, Fujitsu, whatever. They all have 3D enabled laptops, so you can basically get a laptop with a 3D sensor built into it. So basically this is this technology is already becoming a mass phenomenon. And what is nice that in terms of an ecosystem, basically it creates a closed ecosystem where we get acquisition hardware, where we can scan 3D data. We also have repositories. So repositories like, for example, Google 3D Warehouse or Shapeways, which is actually a service that also allows you to print in 3D your 3D scans. So many applications, for example, that Intel works with, like 3D Systems, which is one of the manufacturers of 3D printers. It allows you to scan yourself and then, for example, print yourself in 3D. So forget about selfies, you can think about Shapeys, 3D selfies. So this is, again, this is right now. It's not something that will be somewhere in the future. And many exciting applications. So some of the classical problems in computer vision and pattern recognition, and some more exciting things like reconstruction. So you can, for example, for 3D printing, you can scan yourself from different angles and get a full solid 3D model. Recognition, for example, for robotics, very important. If future robots will be navigating your home, it will be much easier for them to work if they also can perceive depth. Retrieval of geometric objects, so Google does pretty well, I would say very well, text retrieval, much worse image retrieval, and geometric objects are practically not treated. So at some point, probably in the very near future, this will become a major problem and a major opportunity. Avatars, so there is actually in Switzerland, there is a nice company called FaceShift. Basically what they do is real-time animation for a face that looks like this, so it can be anything, actually any animated character that repeats the expressions of your face. And they also were working with our sensors, with RealSense. Virtual dressing, so imagine next time you want to buy a dress, maybe that's more relevant for the ladies in the audience. You don't even need to to get out of your home, because you can do it, just stand or sit in front of your computer, and in real time you could fit a virtual model of the dress and see, for example, to measure the size of your body, to at least to select the right size of your new dress. And of course, gesture control, that's one of the applications that we know already from Minority Report and probably way before. So looking maybe at a little bit broader picture in terms of different fields that are encountered in this field of geometric and visual computing. So image processing, basically that's maybe a little bit naive view of this field, but I think it gets a nice idea of how the fields are separated. So roughly speaking, we can talk about 2D and 3D world. So our world is 3D, right? Objects that surround us are three-dimensional. What we see through a camera or through our eyes actually is 2D, right? That's some projection of the world. So if we live in the 2D world, we talk about image processing in applications like filtering or image enhancement. Imagine that you took a picture with your camera that is too dark. How to improve it? That belongs to the domain of image processing. You can do the same for 3D, for geometry. Imagine that you acquired 3D shape with your scanner, how to clean the noise, how to improve it, how to mesh it, etc. This is geometry processing. Going from 2D to 3D is usually called computer vision. One of the classical applications is how to reconstruct a 3D structure from multiple images, from multiple views. The other way around, when you have a 3D representation of your object and how to render it, is called computer graphics. Again, there is of course some contamination between these fields. You can also think of some higher dimensional abstract world of concepts, and going into this world would be called, for example, pattern recognition and machine learning. Okay? So today I would like to talk mostly about dealing with 3D data, also talking about machine learning and pattern recognition. And if we compare, I don't know what is your background, but probably you're more familiar with signal processing than with 3D geometry processing. If we compare the differences and similarities between images and 3D shapes, then image, at least in 99% of cases, you think of it as a matrix or array of pixels, right? This is what you do with images. If you open a JPEG in Photoshop, it will be represented like this. In case of 3D shapes, it's not necessarily the case. So in many applications, depending on what kind of data or what kind of applications you are dealing with, you might have your 3D data represented as point clouds, for example. This is what usually comes out of some structure from motion algorithms in computer vision. It might be a mesh. So this is what people in computer graphics love, working with triangular meshes or quad meshes, so on. Voxels, so generalization of pixels in 3D. So, for example, in medical imaging applications, this is very common. For example, when you get your 3D data from, let's say, a CT or MRI scan. Level sets, so some implicit representations, usually this comes as a result of some segmentation. So if you have some volumetric representation and you want to segment your shape, so the output of segmentation algorithms usually will be in this form of, for example, sine distance function. Okay, so if we look at the variety of transformations that we need to deal with in image processing, usually it's viewpoint transformations. You want to look at the same object, at the same picture, from a different perspective, and you want to be able, roughly speaking, to say that that's the same object, right? So some viewpoint transformations, usually they're homographies, and at least locally you can simplify them as affine transformations. In 3D shape analysis, we are usually interested in non-rigid deformations, like, for example, our body. If we want to analyze it, it can deform in any way. Question?
Yeah. Well, not rather a question, but just an addition. In image analysis, non-rigid deformations are equally important. For example, in movies industry, facial transformations which are non-rigid at all are very important.
Sure. So I didn't claim otherwise. I think basically the main difference that you lose one dimension when you go from 3D. So it's still a 3D object that deforms, but when you image it with your camera, you still have non-rigid deformations that you need to deal with somehow. Yeah. So it's obvious. Right? But at least classical computer vision applications, like, for example, design of image descriptors, usually the property that you want is affine invariance, which is a local representation of viewpoint transformation. Okay. Now, another thing is the question of correspondence. In two images, for example, you can easily define what is one image plus another image, or you can subtract or deal with images basically as vectors. Okay. It's not the case with non-rigid shapes. So you can easily say what will be half of Mona Lisa plus half of Spring of Botticelli. And it's very hard to say, or at least it's not obvious to say what will be half of this horse plus half of this horse, right? So you need some correspondence which is usually obvious in images, at least in this case, they are brought to some common system of coordinates. In this case, it's not the case, right? It's not very obvious what would be the common system of coordinates for non-rigid shapes. So today I actually wanted to talk about something that is called spectral geometry, which is a kind of umbrella that encompasses many problems in 3D shape analysis. And it's based on a very simple, at least conceptually, notion of spectral analysis of some Laplacian or Laplacian-like operator. Okay, so if this formula tells you something, right? Basically what you see here are eigenfunctions and eigenvalues of some operator that we call the Laplacian. Okay, so all the structures that you're able to derive from these eigenvalues and eigenfunctions, we call them spectral geometry. Okay, very roughly, maybe it's not exactly a correct definition, but it's probably the easiest way to explain it. Okay, why actually this kind of methods is interesting? First of all, it's representation independent. Almost representation independent, right? Basically, if you have your 3D shape that is represented as, let's say, a mesh, or a point cloud, or maybe a set of voxels, or a sine distance function, doesn't matter. If you're able to compute a Laplacian operator on this kind of data, then more or less you're done, because all the rest is the same. You will need to compute its eigenfunctions and eigenvalues, and then all the rest looks exactly the same. Okay, so we operate with these structures. What is also nice, as I will explain, this construction will be intrinsic, meaning that it is defined using the local metric structure of the shape itself. As a result, it will be invariant to what we call isometries, to deformations that do not stretch or tear the 3D surface. Okay, and it's also computationally efficient. Also, what is nice, well, again, I don't know what is your background in terms of signal processing, but many of the notions that that can be defined in terms of eigenfunctions and eigenvalues of Laplacians have actually very nice and clear analogies in classical signal processing, frequency analysis or Fourier analysis. Okay, so kind of structures that I would like to talk about today will be local descriptors. So we want to describe, for example, what happens around this point on the nose of the horse. Global descriptors, so basically some vector of numbers that captures the entire object, so that will tell us that this is a horse and maybe an elephant will have a different descriptor. A variation on the same thing, stable regions, basically instead of point-wise descriptors we'll have some regions, some segments of the object, and the intrinsic distances. So we'll be able to measure distances between points on the object itself. So why these structures are important? For example, the problem of shape similarity. I would like to say whether these two objects are similar or not. We can compute local descriptors, we can aggregate them into a global descriptor. For example, one of the common techniques that is used in computer vision is called the bag of features. So basically you count the frequency of occurrence of different descriptors in your object, and then we can just compare these global descriptors. Okay? So similarity is one of the prototypical problems in shape analysis. Another prototypical problem is shape correspondence. So in shape correspondence, for example, we can quantify the quality of a correspondence by asking how well it preserves the distances, for example. So if we have a pair of points on this horse, the corresponding pair of points will have a different distance. Okay, so the difference or the discrepancy between these distances could tell us whether the correspondence is good or not. So I don't know if in theoretical math and metric geometry, you might have heard about the notion of Gromov-Hausdorff metric. So basically, this is one of the settings of this problem. Okay, so briefly, the outline, I would like to remind you maybe some of the background that you probably know from calculus, and what is a Laplacian, and actually how it generalizes to manifolds, to surfaces. Then I would like to again give some background in spectral analysis, how you do basically Fourier decomposition on manifolds. Then we'll talk about heat diffusion. So heat diffusion will be one of the important problems that actually involves the Laplacian, can be solved in the spectral domain. It will give rise to some important spectral structures like diffusion maps, metrics, and also sublocal descriptors that we'll call the heat kernel signatures. Then I would like to talk about learning. So this is some pretty recent results that we are working on, and that's basically the adaptation of the popular and famous framework that is called convolutional neural networks. That is very, very hyped today in computer vision community. How to do this kind of stuff on manifolds, on non-Euclidean objects. And then basically a variation of the same framework when we can do localized Fourier analysis using windowed Fourier transform in manifolds. And then at the end I would like to talk about correspondence. Okay? So I guess it might be a bit ambitious program because we have about 3 hours and probably I'm a little bit slow. Okay, so let's talk about the Laplacian operator, right? I guess for many of you it will be just a reminder. So let me try to explain what is a Laplacian in 1 minute. Okay, so imagine that you have some domain and a scalar field defined on this domain. So example, let's say your domain is this room, right? So 3-dimensional space, and you can measure temperature at each point of this space. Okay, so basically this scalar field will be the temperature. And for example, standing probably here near this projector, it will be hotter. Probably at the back of the room, it will be colder. Okay, so let's represent it with different colors. So blue will represent low values of temperature and red will represent high values of the temperature. Okay, now what is the gradient of this field? Basically, roughly speaking, it tells us the direction of the steepest increase of f, the scalar field, at point x. Okay, so it can be represented as an arrow, and this arrow will point to infinitesimally the direction that will, if I move in this direction from my point, I will increase or decrease the temperature the most. Okay, so this is the gradient of this scalar field. Now, that's already called the vector field, right? So basically, the gradient at each point is a vector. And if we have a vector field, let's denote it by F capital, the divergence of a vector field is the density of an outward flux of this field from infinitesimal volume around X. So again, roughly speaking, it allows us to define what is a source and what is a sink, right? So basically, some point from which heat flows or point into which heat flows. Okay, and we have the famous result that has many names. Let's call it the divergence theorem that actually relates the integral of divergence of a field over a volume with integral of the field on the boundary of this volume. Okay, basically what it says informally that if you want to get a net flow through some volume in space, then you need to sum up the sources and the sinks. Okay, so that's the divergence theorem. Unlike the previous definitions, it's global, so you can work with big volumes. Okay, not with the infinitesimal quantities. Okay, so what is a Laplacian? We define it as, so it depends on the application. In physics, usually define it with plus. Here we want to define it with minus. So just have it in the back of your mind that our Laplacian is defined with minus with respect to probably the definition that you're used to. And basically, it tells us roughly the difference between the average of f on some infinitesimal neighborhood of a point and the value of f at that point. Okay? So, and you can basically derive this definition as a consequence of the divergence theorem. Okay? Now, the Laplacian is really a ubiquitous thing. You can encounter it in physics, in mathematics, practically everywhere. Okay? One of the examples is heat equation. Okay? I guess you've seen such a thing several times. And basically what it represents is what is called the Newton's law of cooling. Okay, which tells us that the rate of change of the temperature of an object is proportional to the difference between its own temperature and the temperature of the surrounding of this object. Okay, so that's exactly what we see. That's the rate of the change of the temperature, the derivative of f with respect to time, right? And on the right-hand side, we have the Laplacian. That, I remind you, is just the difference between the temperature at a point, or any value of your scalar field at a point, and the surrounding. Okay. Now, C is called the thermal diffusivity constant. For simplicity, we'll assume it to be 1. Okay, you just need to pay attention that the units are correct. Okay, so this is heat equation. You encounter it in many cases. In quantum mechanics, for example, Schrödinger equation involves the Laplacian. Different applications, for example, in waves, when you model propagation of waves, it also involves the Laplacian, and so on. Okay, we'll see some of these later on. Okay, now let me try to explain Riemannian geometry in 1 minute. So basically, when we want to adapt the same structures to non-Euclidean domains, to surfaces, we need to, the main thing that we need to have in mind is that a surface is only locally Euclidean. Okay, we don't actually have a global system of coordinates in most cases. So basically, our Euclidean model for the surface is called the tangent plane. Okay, it's local flat representation of our surface. So let's denote it by T of x. Okay, and Riemannian metric, it's nothing else but the inner product in this space. Okay, basically it's a way of measuring distances locally in the tangent plane. Okay, and it must depend smoothly on the point. So if I move from one point to another point, the metric, the inner product, will not change dramatically. Okay, so it is smooth. Okay, what is isometry? It's a transformation of the shape that preserves the metric. So for example, if I take a piece of paper, right? If I bend it in different ways without stretching it, I cannot stretch paper, right? Or I cannot tear it. Any deformation of this kind will be an isometry. It preserves distances. Okay, that's basically, in Greek, isometry means equal distance. Okay, let's define another technical thing, what is called the exponential map. So it's a way of moving from representation in the tangent plane back to the manifold, okay, to the surface. So if I have a vector in the tangent plane, let's denote it by V, exponential map will take me back to the manifold, to the surface. Okay, so it's a kind of projection.
Why is it named exponential?
It will be a long explanation. Okay. So it is related to the exponential. It is to the exponential function. So basically, the inverse of it is called the log map. Okay, it will be it will be a long bracket. So let's maybe discuss it afterwards. Okay. Another important thing is a geodesic. So it's the shortest path between between 2 points on the manifold. Okay, and in the Euclidean space, it's just the straight line. In general, in Riemannian geometry, first of all, it's not unique. So think of a sphere. There might be infinitely many geodesics within a pair of points. But it's always the shortest path, or a shortest path. Okay, now back to our differential operators. So imagine now we have a scalar field that is defined on our surface. Okay, so in order for the previous definitions to work, we just need to map it to the tangent plane. Okay, and for this purpose we use the exponential map. So we compose our field with the exponential map, we get a scalar field in the tangent plane. Okay, we can define the gradient as just a standard Euclidean gradient of this composition of f with the exponential map, taken at the origin of the tangent plane, at the vector 0, okay, which is the point x here. Okay, we call this the intrinsic gradient. And as the standard gradient in standard calculus, it allows us to do Taylor expansion, in this case of first order. So we can approximate the function in this way, right, where the first order term is exactly the inner product of the gradient with a vector in the tangent plane. Okay, so the intrinsic gradient is a vector in the tangent plane. We can also define the Laplacian, which in Riemannian geometry is called the Laplace-Beltrami operator, exactly in the same way. So it's Laplacian of this composition of f with the exponential map. Okay, and it has a bunch of nice properties. So first of all, it's intrinsic, so you can describe it in terms of the Riemannian metric only. Okay, which means that it will be invariant to isometries. So if you deform your shape, the Laplacian will remain the same. And it's positive semi-definite, so it has no negative eigenvalues. We'll talk about it in a second. Okay. Now, it might be easier actually to think of Laplacian when you think of discrete structures. And at the end of the day, we work always with discrete data, so we don't have anything continuous. So continuous is, let's say, is a mathematical definition, and in practice, we need to work with discrete Laplacians. So in one-dimensional case, again, remember that we define Laplacian with minus sign. It's just the difference operator, second order difference operator that looks like this. So if we want to compute the Laplacian at this point, just need to take twice the value of the function at this point minus the value at the point to the left and the point to the right. Two-dimensional case, more or less the same thing. Okay. In general, we don't need to work with regular grids. We can define Laplacian on a graph. So if you have a weighted, undirected graph, for example, a social network, let's say, then we can define a version of Laplacian that is called symmetric unnormalized Laplacian in this way. Okay, so it's exactly the generalization of what is shown here to unstructured data. Okay, there are many ways of defining Laplacians on graphs. This is one of the ways. Okay. Now, if we want to work with geometric data with meshes, in particular with triangular meshes, in computer graphics there is a very popular way of discretizing the Laplacian, which is called the cotangent formula, and basically it looks at the it takes the average of the cotangents of these angles that are positioned in front of this edge, okay, of the mesh, and basically it looks very much like the like the discretization of the Laplacian for the graph. The only difference that this is consistent. So if under some technical conditions, this will converge to the true continuous Laplace-Beltrami operator. Okay, the graph Laplacian usually will not. Now, in order to convince yourself that this really is an intrinsic operator, you can also express the cotangent formula using the discrete metric. The discrete metric is basically one of the ways of discretizing the metric is taking the edge lengths of your mesh. Okay, so that's the discrete version of the Riemannian metric. You take the length of the edges. You can express these cotangents in terms of the edge lengths only. The areas that we had before here can be expressed using the Heron's formula in this way. So it is expressed entirely in terms of the Riemannian metric, which is, at least, I have not encountered often in the literature, but it's useful at least to convince yourself that this is true. So it's really intrinsic. Okay.
What is AI?
Sorry?
What is A?
So AI is some local area element. The simplest way to define it is just take the sum of all the areas of the triangles divided by 3. Okay, so it's the area of discretization of the area element at this point I.
Area.
Yeah, that's area. Okay, and also the units are also of area, so you can check that the units here are correct, right? So it has units of length squared. Okay, now when you do computations, you can actually represent the Laplacian as a sparse matrix that will look like this. So the function on the mesh will be represented as an n-dimensional vector, n is the number of vertices. A is the mass matrix, so it's diagonal matrix containing the area elements. So you can think of it as a matrix that scales your inner product on this space. And W, this cotangent formula, actually defines what is called in physics, the infinite elements, the stiffness matrix. Okay. And D is just a diagonal matrix that contains the sum of the off-diagonal elements. Okay, so bottom line, it's big but sparse matrix. Okay, so what are the properties of Laplacians? One of them, of course, the constant function is an eigenfunction, right? If you apply the Laplacian to a constant function, you will get 0, right? Which is, you can think of it as 0 multiplied by the function itself. So it's an eigenfunction with a corresponding 0 eigenvalue. Okay. And basically, in the discrete case, it's satisfied by the construction of the Laplacian. Remember that this is how we define the Laplacian. If you take f constant, then you will get 0 everywhere. Okay. Now, the continuous Laplacian is a symmetric operator, so meaning that it you can write the equivalence between these inner products. And in the discrete case, it means that the matrix L, the Laplacian matrix, must be symmetric. So it equals to the transpose of itself, and this will give us real eigenvalues and orthogonal eigenvectors. That's the properties that orthogonal matrices have. Symmetric matrices have. The operator in the continuous case is local. It means that the value of the Laplacian at point x doesn't depend on f at x prime, where x prime is some distant point. Okay, and in the discrete case, we can interpret it as that the weights wij will be 0 if ij are not connected by an edge. Okay. Another property, well, it might be slightly more difficult to explain. Think of Laplacian as a second-order differential operator, right? If you apply it to a linear function, you will get a 0. Okay. So more accurately, we can define that if x is a plane and f is a linear function, then the Laplace-Beltrami operator of this function will be 0. Okay. And equivalently, in the discrete case, we can write it in this way. Okay, so when L is applied to the embedding coordinates of the surface, then we'll get a 0. And physically, the interpretation is that you can think of it as a bending energy of a plate of some surface, and plate will have 0 bending energy. Okay. We said already that the Laplacian operator, the continuous one, is positive semi-definite. And in a discrete case, it just means that the matrix L is positive semi-definite. So it has no negative eigenvalues. Another important thing, maximum or minimum principle, harmonic functions that satisfy that the Laplacian of f are 0 have no maxima or minima in the interior of x. Okay, so in cases when our surface has boundaries. And in the discrete case, it can be shown that this is equivalent to having positive weights. So WRJs are non-negative, and there is at least one strictly positive weight for each vertex. Okay, and also it's relatively easy to show that when you have this property of positive weights plus symmetry, you also get positive semi-definiteness. So it follows automatically from combination of these two properties. Okay, and of course, final property is convergence. Basically, you can define it in different ways, convergence in different senses. But for us, what is important that if you have some PDE that is discretized with this discrete operator, then the solution of this discrete PDE will converge to the solution of the continuous PDE partial differential equation under some technical condition when the number of vertices will go to infinity. Okay? Technical conditions usually imply that you don't get infinitely thin triangles, so some bad discretizations of your surface. Okay, now there is probably a zillion of different discretization of Laplacians. Here I listed just 4, so it could be combinatorial Laplacian that you define on a graph, cotangent formula showed there is also what is called a mean value Laplacian, intrinsic Delaunay Laplacian, many other discretizations. And here are the properties that we listed before, and you can see that some Laplacians satisfy some of the properties. So for example, the cotangent formula that is used ubiquitously in computer graphics, it is symmetric, it is local, it has the linear the linearity property, but the weights are not positive. Actually, the cotangents can become negative. It is positive semi-definite, and under some technical conditions, it's convergent to the continuous operator. The question is, out of these many discretizations, is there one that satisfies all the properties? So what do you think? So this is actually quite non-trivial question. It was answered only in 2007, paper of Vardetsky and Kosras. And they call it the no free lunch theorem. Basically, they show that these properties cannot be satisfied simultaneously. So you need to sacrifice something. And basically, I would say, if you ever need to discretize a Laplacian or choose a discretization, choose it wisely based on the problem. So in our case, actually, I will show that it makes sense to use the cotangent discretization. It is symmetric, so it will give us, basically we are interested in spectral properties of these matrices. So we want real eigenvectors, real eigenvalues. We want orthogonal eigenvectors. So positive semi-definiteness is also important because we'll also be looking at properties that are expressed for eigenvalues of the Laplacian. So for us, this is a good representation, but don't take it for granted. If your problem, for example, requires, let's say, the maximum or minimum principle, then probably that will not be necessarily the best candidate. So you might use something else. Okay, so let's now talk about spectral properties of Laplacians, and one of them will be let's start with Laplacian eigenvalues. Okay, and for this purpose, let's do the following experiment. So take a plate and apply to it acoustic vibrations. Okay, so there is some vibrating thing underneath the plate, and we put a thin layer of sand on top of this plate. And you can see that at some frequencies, the sand forms these patterns, okay, and they're stable, okay? If you change the frequency, you will see that the patterns will change. You see it? Now the pattern became different. Okay, and now again it became different. So let's stop it here because the sound is pretty unbearable. So this is a modern reinterpretation of a classical experiment that was done by German physicist Ernst Chladni more than 200 years ago. And this is a drawing from his book on the theory of sounds that shows how the experiment was done in that time. And basically, Chladni at his time, he didn't know exactly what is the mathematical explanation for this phenomenon. So he saw it more as an artistic way of visualizing the sound. But now we know basically that what we observe are actually vibration modes, which are eigenfunctions of the Laplace-Beltrami operator, and they are solution of what is called the Helmholtz equation, which is the stationary part of the wave equation. So basically what we observe are standing waves. So basically the grains of sand jump because the plate vibrates, but at some points basically there are zero crossings that are stable, so the grains do not jump. So the wave oscillates, but at some point it has a fixed zero crossing. So these are exactly where the contours are formed. Okay, so there are some resonant frequencies the eigenvalues of the Laplacian that correspond to these particular behaviors. Okay, and the patterns actually, the contours that you see are zero crossings of the corresponding eigenfunctions of the Laplacian. So basically, the Laplacian, which is we started with some kind of local averaging operator, it has this nice physical acoustic interpretation. Okay, so we could try to use it in shape analysis, right? So we know that the Laplacian is deformation invariant, right? So obviously all the structures that are derived from the Laplacian, the eigenvalues and eigenfunctions, will also be deformation invariant. Let's try to describe our shapes in terms of the eigenvalues. So here is a plot of the first 100 eigenvalues of 3 different deformations of a horse. Okay, you see how they look like. And these are deformations of the monkey, and these are deformations of the human. So you see that by looking at the eigenvalues, we can pretty easily distinguish between monkeys and humans, for example.
What's on the axis?
So that's the number of the eigenvalue.
Number of what?
The index of the eigenvalue. So what I'm showing is the first eigenvalue, the second eigenvalue, and so on. So maybe what is misleading that I'm plotting as curves, it should be just single points.
On the y-axis?
It's the value, so it's lambda i's. Okay, so basically the plot is slightly misleading because it should be discrete values. Okay, and this is a work of Martin Reuter back from 10 years ago. They call it the shape DNA. So basically they use Laplacian eigenvalues to characterize basically as a shape descriptor. And they show applications in shape retrieval. Okay, so obviously when two shapes are isometric, they will have the same Laplacian, right? So they will have the same spectrum, the same eigenvalues. Okay, so we call such shapes isospectral. Do you think that the opposite is true? If two shapes are isospectral, they have the same spectrum, will they have the same Riemannian metric? So the question was formulated by Mark Katz in '66. And the way that he described it, can you hear the shape of the drum? So basically, think of a shape as a drum, right? And basically, the eigenvalues convey some acoustic properties of this drum. By hearing the acoustic properties of the drum, basically by observing the eigenvalues of this shape, can you recover the structure, the intrinsic structure of the shape, which is the Riemannian metric? So do you think it's possible?
I would expect a finite number of solutions.
So first of all, infinite number of solutions, all possible isometries. So let's say take a piece of paper, it has infinitely many actually continuous isometries, right? So basically we are interested in the metric itself. So basically all the embeddings that will have the same metric, we don't care about them. We are interested only, so basically we'll say that all these are equivalent, right? If the metric is the same.
A finite number of classes of isometric solutions.
So basically you are saying that we cannot recover the metric from the spectrum. That it will be ambiguous.
In a unique manner, I think no.
Okay, so then you're right. Okay, but let's, basically it was a question that occupied theoretical mathematicians in this field for many years. And for example, some works that looked at the heat trace, we'll talk about heat operator in a few minutes. Basically, if you look at the sum of the exponentials of the eigenvalues of the Laplacian, you can try to express it as power series, okay, with some coefficients. So actually people worked hard to express these coefficients. And you can see, for example, that the zeroth coefficient is the area of your manifold. The first coefficient is the total Gaussian curvature, the integral of the Gaussian curvature. And you can also relate it by the Gauss-Bonnet theorem to topological structure, to the Euler characteristic of the shape. But can you get the metric from these coefficients? Okay, so the answer is negative. The first counterexample was given in '92. And these are two isospectral but non-isometric shapes. So in this case, they're flat, two-dimensional. Basically, what makes them non-Euclidean is the boundary. So in this case, we also have some boundary conditions. And you can also find some other higher dimensional examples. So basically, it's actually not exactly well known what is the class of ambiguity that we have here. So in this case, these examples, they come in pairs, these two-dimensional structures. So you have pairs of isospectral but non-isometric shapes. Okay, so going back to that property of to this shape descriptor, the shape DNA, it means that there might be shapes that are completely different, but they have the same spectrum. So potentially this descriptor is ambiguous. Okay. Let's now look at the Laplacian eigenfunctions. So we looked at eigenvalues. Let's see what are eigenfunctions. So here's a visualization of the first 4 eigenfunctions. The first one is constant, right? It corresponds to the zeroth eigenvalue. And these are the first non-trivial eigenfunctions. So here are the cold colors represent negative values and hot colors represent positive values. So it basically looks, first of all, you see that it localizes at some protrusions. And if you increase the number of eigenfunctions, we'll see that the number of zero crossings, basically, moving from positive to negative value will increase. So you can think of it as kind of frequency. So you can think of eigenvalues as frequencies, and the corresponding eigenfunctions will see exactly what they are. Okay. Now, what is nice that eigenfunctions are invariant to isometric deformation. So if I deform this shape, I will still keep the same eigenfunctions. Now you can see the footnote here, which says up to some ambiguities. Actually, these ambiguities are important. We'll see later that in some cases they're quite a complication, in some cases they're helpful. For example, they allow us to describe symmetries of these shapes. Okay? So one of the ambiguities you can think of is sign. If phi is an eigenfunction of the Laplacian, then minus phi is also an eigenfunction. Okay? That's the most obvious ambiguity. But if, for example, the eigenvalue has multiplicity, then you can already not talk about eigenfunctions. There will be some subspace of your eigenspace and any basis that spans this subspace. So basically, a rotation in this subspace is the ambiguity. Okay? Now, using eigenfunctions, we can do Fourier analysis. And just a reminder, if you have a function, standard function, let's say on an interval between minus pi and plus pi with real values, you can write it as Fourier series. Okay, so take basically these will be the Fourier coefficients, right? That's inner product of the function with complex exponentials, right? That look like this, sines and cosines, and sum these coefficients multiplying by the basis functions, you will get back the function itself. Okay, so that's forward and inverse Fourier transform. Now, for some reason, well, I don't know, maybe here it's different. When I was studying Fourier analysis, nobody actually told me that these basis functions are eigenfunctions of the Laplacian. You can easily verify that if you take second order derivative in this one-dimensional case of your exponential complex function, you will get back the same function up to the frequency squared. Okay, so basically the frequency squared will be the corresponding eigenvalue. So this actually gives a very natural generalization of the Fourier analysis technique. Instead of the classical Euclidean Laplacian, you can take the Laplace-Beltrami operator, right? And the eigenvalues of the Laplace-Beltrami operator will play the role of frequency. So
did I get right that we use the eigenfunctions instead of harmonic functions?
Exactly. Exactly. So they are orthogonal, right? Our Laplacian is symmetric, and the corresponding eigenvalues can be roughly interpreted as frequencies. Okay, so looks exactly the same way, just the inner product has changed. Now it's an inner product on the surface. Okay.
Does this modification have its own name, like there is a current name for wavelength analysis? Does this one have its own name?
Fourier transform or generalized Fourier transform.
Generalized.
Yeah. So basically, it's still the Fourier transform, right? Fourier transform is not necessarily defined in this way. It can be any orthogonal basis. So you have a Hilbert space, right, which is space of functions with an inner product that is defined on the manifold, and basically this is some orthogonal basis. Okay, so it's still Fourier analysis, just done on a different space. Okay, now in the Euclidean case, we have a nice thing that is called convolution, right? And we have the nice property that Fourier transform diagonalizes the convolution operator. This is usually called in harmonic analysis or signal processing the convolution theorem, right? The fact that if you take Fourier transform of two functions, and if you want to describe their convolution, you just take the product of their Fourier transforms and take the inverse Fourier transform, right? So you can define by analogy the generalized convolution as exactly the same thing. So I take the Fourier transform of the first function, the Fourier transform of the second function, right? I get Fourier coefficients, I multiply them, and I take back the inverse Fourier transform. Okay, so this is the product in the Fourier domain. That's the inverse Fourier transform. In the Euclidean case, it will give us convolution. Okay? In the non-Euclidean case, you can think of it as a generalization of the convolution. What is lost, of course, here is shift invariance. The classical convolution is shift invariant. The generalized convolution is not. Okay, so let's now talk about heat equation. We mentioned it already in the beginning. Let's mention it again. And I guess this will be, again, a reminder of some standard techniques that you studied in free analysis or in calculus, but I think it will give an important analogy to analysis and heat equations on manifolds. Okay, so let's solve heat equation on the circle, so one-dimensional sphere. I don't want to deal with boundary conditions, so that's the main reason why to do it on the circle. Okay, so this is how it looks like. So this is our heat equation. Again, the Laplacian here is just second-order derivative, defined with minus, and we also have some initial condition, heat distribution at time 0. So this is how it will look like. Okay, we start with some heat distribution, and basically here the distance, the radius represents the value of the temperature at the point. You see that basically it becomes uniform on the circle. Okay, so the solution is temperature at point theta at time t. And the usual way of solving this heat equation is to assume that the solution is separable. So we can write it as a product of a function that depends only on the spatial coordinate and a function that depends only on the temporal coordinate. And if we plug in this kind of form of the solution into the heat equation, we get something like this. After some rearrangement, this is what we get. Basically that these ratios are constant. Let's call this constant minus lambda. What we recognize immediately here that basically in order for the solution to satisfy the heat equation, these thetas and t's must be the eigenfunctions of the respective operators, of the Laplacian operator and the temporal derivative. Okay? And we know what are the eigenfunctions of these operators. For the Laplacian, that's the complex exponential. For the temporal derivative, that's the Gaussian. Okay? And in both cases, the eigenvalue is n squared. So the basic solution will look like this. So it's a product of a Gaussian and the complex exponential. Now, the equation, of course, is linear. So because of linearity, any linear combination of the solutions will also be a solution, right? So how is it possible that the equation has infinitely many solutions? We also need to satisfy the initial conditions. So out of all these possible solutions, we'll select one. Basically, we select the solution by determining these coefficients A such that it satisfies the initial condition. Okay, and basically that's the requirement that U at theta 0 must be equal to V theta, right? The initial solution. And if we express the initial solution, the initial condition in our orthogonal basis, right? Let's write explicitly this inner product as an integral. Then again, under some technical assumptions, we'll switch the integral and the summation. Okay, and this is called the heat kernel. Okay, so you see that it's a function that depends on the parameter t, and it's a function of theta minus phi. Okay, the difference of two coordinates. Okay, now what is written here? That's an integral of a function v of phi with some function h of t minus phi. What is written here? How is this guy called? That's convolution, right? So that's convolution of v with the heat kernel. Okay. And now, what it means that we can express the solution in form of a convolution, it means that it's shift invariant, that if u theta t is the solution of the heat equation with initial condition v theta, then if we move the initial condition by theta 0, then the solution will also move. Okay? And as I said, h is called the heat kernel, and you can think of it as the impulse response to initial condition that looks like a delta at point t. Okay? You can also interpret it physically as the amount of heat that is transferred from point t to point phi in time t. Okay? We can also define what is called the heat operator, which is just takes the initial condition, convolves it with the heat kernel, and spits the solution of the heat equation at time t. Okay? And it's easy to verify that the heat operator has the same eigenfunctions as the Laplacian. Just apply the heat operator, which is expressed as convolution. Again, do the same mathematics here, exchanging the integral and the summation, right? We know that the eigenfunctions are orthonormal. So here, this is equal to delta, right? It's only 1 when n equals to m. And what we get out is the same function with the eigenvalue equal to e to minus m squared t. Okay? So same eigenfunctions, different eigenvalues. Okay, so you can think of it as an exponential operator applied to the Laplacian. Okay, and we can write it like this. Okay, so exponential that is understood in the operator sense. Okay, if you think of it as a matrix, you do the eigendecomposition of the matrix, you do the exponential of the eigenvalues and compose it back. Okay, and technical details that it's compact and self-adjoint, which is important for some properties to hold. Okay, if you have signal processing.
Can you please remind what is self-adjoint?
Self-adjoint is equivalent to being symmetric, basically. In terms, if you think of it as a discrete representation. So, if you have signal processing intuition, you can think of it as a linear shift invariant system. So you put as input a delta function, and you get something. Okay. If you put some other signal as an input, you will get a convolution with the heat kernel, right? Basically with the impulse response to a delta. Now this is shift invariance, right? This property is very important, and when we see a heat flow on manifolds, we'll see that this property unfortunately is lost. So this is an example of how heat flows on this body. Okay, let's see it again. You see that there is some initial distribution of heat and the heat propagates. So you can actually see that the heat propagates differently at different points of the surface. Even though the speed of the propagation is constant, it's actually equal to 1, right? The diffusivity constant. You see, for example, that in the ears and the tail, it's harder for the heat to escape. Okay? And basically this is the interesting part of heat equations on manifolds. So the heat equation looks exactly the same. We just replace the standard Laplacian with the Laplace-Beltrami operator. Okay? And again, the solution is expressed through the heat operator. You can write it like this, so exponential of the Laplace-Beltrami operator. Let's write it in the frequency domain. So we can express V using the Fourier series, right? So in the frequency domain, we just apply basically this exponential to the eigenvalues of the Laplacian, right? Let's write our inner product explicitly, okay, as an integral, and this is what we get, okay? So this is now the heat kernel. You can see that it's now a function of two variables, x and xi. Before it was a function of their difference. So that's where the shift invariance is lost. In the previous case, we had here dependence on x minus xi, and we could write it as a convolution. Here, no convolution anymore, right? So basically what it means that the heat kernel will change as we move around our manifold. So you can think of it in terms of filtering. If in the Euclidean case, we could just think of it as a linear filter, here the filter is nonlinear. Okay, so the kernel of the filter will change. Here is an illustration. This is how heat kernel looks like at different points of the surface. So you see that it looks differently, so it changes as we move around.